Today, we will talk about the gyroscopic system, which is used in some of the basic flight instruments, also known as the six-pack. As we know from previous videos, the airspeed indicator, the altimeter, and the vertical speed indicator use air pressure to give their indications by means of the pitot static system. While on the other hand, the attitude indicator, the heading indicator, and the turn coordinator use gyroscopic principles to give their readings by means of the gyroscopic system, which we will discuss in this video. With this in mind, we must say that each of these instruments has its own internal gyroscope, specially arranged to measure a certain parameter. But before we go into detail with each one, let's see what a gyroscope actually is. A gyroscope, often abbreviated as a gyro, is any symmetrical body rotating at a speed sufficient to experience the gyroscopic effects. This is a very basic description. Since according to this, we could say that a bicycle wheel, a propeller, or a dedicated gyro are all examples of gyroscopes. As we can see then, the design of a gyro can vary greatly depending on its use and application. However, they all have some components and characteristics in common. In essence, every gyroscope is composed of a rotor that spins at a high speed, the spin axis of the rotor, one or more gimbals, and the frame that supports the gyro. This particular design allows the gyro to have freedom of movement on all three axes, and therefore it is known as a free gyro. Now, when the rotor is not moving, nothing happens, and the gyro behaves like an ordinary object. However, when it starts spinning, it begins to experience the gyroscopic effects. These effects are rigidity in space and precession. Let's take a closer look at each of these, starting with rigidity in space. This establishes that when the rotor of the gyro spins, it remains in a fixed position in its plane of rotation, regardless of the movement of the gimbals or the frame, as we can see in this example. Here, although the gimbals and frame move, the rotor remains rigid in space. We can better appreciate this effect with this other example. Here, as we can see, independently of the movement of the frame or the gimbals, the rotor maintains its axis of rotation rigid in space. Now, the degree of rigidity of the gyroscope is directly proportional to its rotational speed, or RPM, and its moment of inertia. This means that the faster the rotation of the gyro, the greater the rigidity in space and vice versa. We can even experience this in everyday life when riding a bicycle. Since in this case, if we ride the bicycle at a low speed, the wheels will spin slowly, which means that they will present less rigidity in space, and therefore the bicycle will be less stable. On the other hand, if we ride the bicycle at a higher speed, the wheels will spin faster, and therefore they will present more rigidity in space, making the bicycle more stable. Now, the other factor that affects the rigidity in space is the moment of inertia. Basically, this means that the greater the mass and effective radius of the rotor, the greater the rigidity in space and vice versa. As we can see in this example, the mass of the rotor is concentrated in the outer part. Because if we want to obtain the highest moment of inertia, the mass should be located as far away from the axis of rotation as possible. In other words, the larger and heavier the gyro rotor is, the more rigidity in space it will have. This can also be experienced on a bicycle, because if we ride a bicycle with small wheels, they will present less rigidity in space, and therefore less stability. While if we ride a bicycle with bigger wheels, they will present more rigidity in space, and therefore the bicycle will be more stable. In general terms, we can say that the gyroscopes installed in aircraft instruments spin at about 18,000 RPM, have an effective radius of about 2 centimeters, and are heavy. Therefore, we can expect this type of gyros to have a high rigidity in space. With this being said, let's continue with the other gyroscopic effect. The precession. This establishes that any force applied perpendicularly on the plane of rotation of a gyro will be exerted at 90 degrees in the direction of rotation. This may sound a bit complex so far, but let's take a look at a couple of practical examples. In the right side we have a rotating disc, which will represent the gyro. Now, let's suppose we apply a force at this point. According to the precession effect then, this force will actually be exerted at 90 degrees in the direction of rotation, it is, at this other point, which will cause the disc to tilt in this way. Let's look at another example. Here we have a gyro with its axis of rotation positioned horizontally. Now let's suppose that we apply a force at this point. Due to precession, this force will actually be applied 90 degrees in the direction of rotation. It is, in this other point, which will cause the gyro to tilt this way. Now, we have to mention that the magnitude of the precession is directly proportional to the applied force and inversely proportional to the rotational speed. This means that the faster the rotation of the gyro, the smaller the precession and vice versa. And on the other hand, the greater the force applied to the gyro, the greater the precession and vice versa. Up to this point we have already explained what the two main gyroscopic effects are. Now let's see what are the different types of gyroscopes we can find. In essence, gyroscopes can be classified into displacement gyros and rate gyros. And at the same time, displacement gyros can be divided into free gyros and tied gyros, among which we can highlight the Earth gyros. Let's see a brief description of each one of these and where they are used, starting with the displacement gyros. Let's start with the free gyro, also known as space gyro. This is a gyroscope with 3 degrees of freedom, which means that it can rotate freely around the 3 axes. And although it is the most widely used to explain the gyroscopic effects, in terms of practical applications in aviation, they are only used in the older inertial reference systems. Let's now move on to the next type of gyro. The tied gyro. This gyro also has 3 degrees of freedom, however it incorporates a control system that keeps the axis of rotation in a particular position. An example of this type of gyro is the one found in the heading indicator. In this case, it keeps the axis of rotation aligned with the yawing plane of the aircraft in order to give an adequate heading indication. Now, a similar variant of this tied gyro is the Earth gyro. The particularity of this gyro is that it incorporates a control system that uses the Earth's gravity to maintain the axis of rotation in a particular position. This type of gyro can be found, for example, in the attitude indicator. In this case, it keeps the axis of rotation perpendicular to the horizon in order to give an adequate attitude indication. With this, we have already seen the displacement gyros. Let's continue with the rate gyros. Basically, a rate gyro only has 2 degrees of freedom, which means that it is restricted in one of the axes. So when it attempts to rotate in the plane that is constrained, the gyroscope will precess, which can be measured by a spring system to obtain the rate of angular variation. This type of gyro can be found, for example, in the turn coordinator, where it is used to measure the rate of turn, or in other words, how fast the aircraft is changing its heading. In upcoming videos, we will look in more detail at the exact principle of operation of the gyroscope of each instrument. So with this being said, let's look at the different systems that can be used to spin the instrument gyros. In aviation, gyros can be driven by electricity or by air. In the electrical system, it is most common to use direct current. And in the air system, either vacuum suction or positive air pressure can be used. Normally, most light aircraft have the following configuration. The attitude indicator and the heading indicator are driven by an air vacuum pump, while the turn coordinator is driven by the electrical system of the aircraft. The main objective of this design is that in the event of a failure in one of the systems, not all gyro instruments are affected. Finally, let's see what practical applications gyros have in aviation. We have already mentioned that lighter and simpler aircraft use gyros in some of the basic flight instruments. However, in the most complex and modern aircraft we can find gyros in other systems such as the gyromagnetic compass, the inertial navigation and reference systems, the yaw damper, the autopilot, among others. We will talk about the heading indicator, also known as the directional gyro. This is one of the basic flight instruments that we will find in any aircraft and its operation is based on the gyroscopic principles. As mentioned in the video about the gyroscopic system, most of the light aircraft have the following configuration. The vacuum pump provides suction to drive the gyros of the attitude indicator and the heading indicator, while the gyro of the turn coordinator is driven by direct current from the aircraft electrical system. With this in mind, let's take a closer look at the heading indicator. This instrument is also known as the directional gyro, and it indicates the current heading of the aircraft in degrees in relation to a directional reference. Usually, the directional reference used in aviation is the magnetic north pole. However, there is a little problem with this. And it is that the heading indicator has no mechanism that allows it to determine the direction of the magnetic north. Therefore, the pilot must tell it where magnetic north is for the instrument to use it as a reference. To do this, the pilot uses the magnetic compass, since it does have the ability to align itself with magnetic north. Then, the pilot must align the heading indicator using the magnetic compass indication. At this point we might think, if we need to constantly align the heading indicator with the compass, why not use the magnetic compass alone? Well, the answer is that as we've seen in previous videos, the compass indication suffers from significant errors during turns, accelerations, maneuvers, or turbulence. And apart from this, its design causes the compass card to move in the opposite direction to the turn, making it difficult to read, especially under high workloads. On the other hand, the heading indicator does not present these errors and is much more accurate, consistent, and easier to read. That's why it is the main instrument used for heading indication. With this being said, let's see the parts of the heading indicator. First, we have a compass rose in the background. Then we have a miniature aircraft in the middle, which will represent the orientation of the real aircraft. The line that extends in front of the aircraft represents the current heading. And finally, in the lower left corner we have a cage and adjustment knob. Let's now take a closer look at the compass rose. A compass rose is basically a graphic representation of the 360 degrees of azimuth, which is printed on the instrument card. Normally, the long lines represent increments of 10 degrees, and the short ones represent increments of 5 degrees. Apart from this, the main cardinal directions are represented by their corresponding letters. For example, the letter N, which represents north, corresponds to heading 360. The letter E, which means east, represents heading 090. The letter S represents heading 180, and the letter W represents heading 270. In the same way, every 30 degrees, a number representing that heading is included, omitting the last digit. For example, the number 3 represents heading 030. The number 15 represents heading 150. The number 30 represents heading 300, and so on. Now, some heading indicators also include relative heading markings. These are reference angles relative to the aircraft's current heading. In other words, the current heading of the aircraft is used as reference, so it will represent 0 degrees relative. Here we can find the markings for 45, 90, 135, 180, 225, 270 and 315 degrees relative. And again, these angles are not measured in relation to magnetic north, but in relation to the current heading of the aircraft. We will see later with some examples how they are used. Now, to finish with the parts of this instrument, some heading indicators also incorporate a heading bug and its corresponding heading knob. This allows the pilot to select a particular heading in the instrument. It is often used as a reference during manual flight, but can also be used in conjunction with the autopilot system. Having seen all this, let's see how to read this instrument properly. Here, as we can see, the line that represents the current heading is on the north marking, which means that the current heading is 0 degrees. If the aircraft now turns to the right in such a way that we have now this indication, we would be flying with heading 060. Now, if the aircraft turns to the left this way, the heading is now 320. In this other situation the heading would be 090. And here the heading is now 285. As we could see, the heading indicator is quite intuitive and easy to read. Let's now see how to use the relative heading markings. Let's say that with this current heading of 285, the ATC tells us to make a 45-degree turn to the right. He is not asking us to turn to heading 045, but to turn 45 degrees to the right in relation to our current heading. Clearly we could add 45 degrees to heading 285 to determine the heading to which we must turn. But it is easier to use the relative heading markings of the instrument. In this case, we just have to look at the 45 degrees relative marking, which indicates heading 330. So we just have to turn to that heading. Now, let's say that the ATC asks us to make a 90-degree turn to the left. In this case, we just have to look at the corresponding relative marking, which in this case indicates heading 240. So we just have to turn to that heading. Having seen how to use this instrument, let's see how it actually works. As we already mentioned, the heading indicator uses the gyroscopic effect of rigidity in space. Specifically, this instrument incorporates a horizontal gyro so that the plane of rotation is perpendicular to the horizon. This gyro has 3 degrees of freedom, which means that it can rotate freely around all 3 axes. This implies that, once aligned with the reference heading, the gyro will remain rigid in space, regardless of aircraft movements, making it an excellent reference to measure the heading. Let's see how this instrument works in practice. On the right side we have the instrument as the pilot would see it. And on the left side we are looking at the instrument from above. In this case, it is indicating a north heading. If the aircraft makes a turn to the right, both the aircraft and the instrument will turn to the right, while the gyro remains rigid in space. This way, the instrument can measure the angle between the directional reference and the current aircraft heading. And the same happens if the aircraft turns to the left. In this case, both the aircraft and the instrument will turn to the left, while the gyro remains rigid in space, allowing to measure the heading correctly. Now, as with other instruments, the heading indicator is not perfect, and therefore it has certain limitations. And it is that, although theoretically the instrument's gyro has 3 degrees of freedom, in reality it has mechanical stops that prevent the gyro from rotating completely freely. This implies that upon reaching excessive pitch or bank angles, the mechanical stops will prevent the gyro from rotating freely, causing the instrument to topple and become inoperative until it is reset by means of the adjustment knob. Typically on electric-driven heading indicators, the pitch and bank limits are around 85 degrees. While on the other hand, on air-driven gyros, the limits are more restrictive, around 55 degrees. Now, this is not the only limitation of the instrument, since it also suffers from gyroscopic apparent wander. Let's see what is this. As we know, when the gyro starts spinning, it remains rigid in space. However, the Earth does not remain static, it rotates at about 15 degrees per hour. To understand how this affects the gyro, here we have the Earth seen from above. Let's suppose we are at this yellow point, and we align the gyro of the heading indicator in such a way that it points to the north. Now, after a few hours, the Earth would have rotated several degrees, so let's say that we are now at this other position. As we can see, as the gyro remains rigid in space, it is no longer pointing to the north, and it has now a deviation of 60 degrees. This implies that the heading indicator will be using a wrong directional reference, so the heading indication will be incorrect. This apparent wander error can be up to 15 degrees per hour near the poles. And it is that the apparent wander is maximum at the poles and minimum at the equator, but let's see why. In the image on the left we can see that near the poles the apparent wander is significant. However, in this image on the right we can see that at the equator, the plane of rotation of the gyroscope remains aligned with the meridians pointing north, regardless of the rotation of the Earth, so then we say that there is no apparent wander at the equator. Based on this, we can deduce that the magnitude of the apparent wander depends on the latitude and can be determined by means of this formula. Now, this wander is known as apparent, since in reality it is not the gyroscope that drifts, but the rotation of the Earth that creates this effect. Now, there is another effect known as real wander. And it is produced since the mechanisms and gears inside the instrument are not perfect, they suffer from wear, friction, and imbalance. That causes the plane of rotation of the gyro to drift due to precession. However, this error is normally small. In well-maintained modern gyros, the real wander is very low, around 1 degree per hour. Taking into account the effects of real and apparent wander, the question is, how do we correct the instrument indication? Well, for that we have to use the cage and adjustment knob. This allows the gyro to be disengaged from the card. This makes the gyro act as a free gyro and does not topple with excessive maneuvers or attitudes, as well as allowing the card to be realigned with the magnetic compass indication. As a general rule, to avoid significant indication errors, the pilot should realign the heading indicator with the compass every 10 to 15 minutes during flight. However, this adjustment should only be made when flying straight and level, with a constant speed, as this is the only situation in which the compass will indicate the heading correctly. Let's see an example of how to reset the heading indicator with the compass. Let's say we are flying straight and level, with a heading of 120. In this case, both the compass and the heading indicator are indicating the same heading. However, due to the effects of real and apparent wander, the heading indicator will drift progressively with time. In this case, now the heading indicator is showing a heading of 110, even though the compass continues to indicate the correct heading of 120. In this situation, the pilot will have to use the adjustment knob to reset the heading indicator according to the magnetic compass indication. But again, this should only be made while flying straight and at a constant speed. Now, up to this point we have seen how a conventional heading indicator works. However, there is a variant of this instrument, known as the gyromagnetic compass, which is also known as the remote indicating compass or the slave gyro compass. Basically it consists of a heading indicator that instead of incorporating a free gyro, has a slave gyro. It uses a system of remote magnetometers to determine the direction of magnetic north, and this way it automatically and constantly realigns the instrument's slave gyro with magnetic north. But we will deal with this instrument in detail in another video. We will talk about the attitude indicator, also known as the artificial horizon. This is one of the basic flight instruments that we will find in any aircraft, and its operation is based on the gyroscopic principles. Now, as mentioned in the video about the gyroscopic system, most of the light aircraft have the following configuration. The vacuum pump provides suction to drive the gyros of the attitude indicator and the heading indicator, while the gyro of the turn coordinator is electrically driven by direct current from the aircraft electrical system. However, we must say that there are other configurations, and therefore the attitude indicator can also be driven by electric current in some cases. With this being said, let's now see what information is provided by this instrument. The attitude indicator, also known as the artificial horizon, is an instrument that measures the attitude of the aircraft in relation to the horizon in terms of pitch and bank. In simple terms, the bank angle is the inclination of the wings in relation to the horizon. And here we can see how it is indicated in the instrument. On the other hand, the pitch angle is the inclination of the nose of the aircraft in relation to the horizon, as we can see in this example. Now, although the indication of the instrument is quite intuitive, let's look at the parts of the attitude indicator. First, we have the miniature aircraft in the middle, and as its name suggests, it will represent the wings and the nose of the aircraft. Then, we have the artificial horizon, represented by this white line, which separates the upper part, which represents the sky, from the lower part, which represents the ground. Now, as we can see, the instrument has several markings and scales, so let's look at them separately, starting with the banking scale. It is located in the upper part of the instrument, where the current bank angle of the aircraft is indicated by the bank indicator, which in this case is this yellow bug. In this particular example, we can see that the wings of the aircraft are leveled, so the bank angle indicated is 0 degrees. The scale has several markings to either side that represent 10, 20, 30, 45, 60, and 90 degrees of bank. Now, something important to note is that this instrument indicates the bank angle only, which is the angle between the horizon and the lateral axis of the aircraft, as we can see here. In this case, the bank indicator is pointing the third marking in the right side of the banking scale, which represents a 30-degree bank to the right. Now, we must bear in mind that this instrument does not indicate whether the aircraft is turning or not. It only indicates the bank angle. The instrument used to determine if the aircraft is turning and how fast it is doing it is the turn coordinator. With this being said, let's continue with the pitch scale. The pitch angle is indicated by this little point in the middle of the miniature aircraft. In this case, as we can see, the point is right on the horizon line, which indicates a pitch of 0 degrees. On the pitch scale, the long lines represent increments of 10 degrees of pitch, either up or down, while the short lines represent increments of 5 degrees. Now, it is important to note that the instrument indicates only the pitch angle, which is the angle between the horizon and the longitudinal axis of the aircraft, as we can see in this image. In this case, the pitch indicator is at the 10-degree nose-up mark, which means that the nose is pointing 10 degrees up in relation to the horizon. Now, another thing to bear in mind is that this instrument does not indicate whether the aircraft is climbing or descending, since it only indicates the attitude of the aircraft in relation to the horizon. The instrument used to determine if the aircraft is actually climbing or descending is the vertical speed indicator. There are different models and designs of the attitude indicator, both analog and digital. And although they have slight differences, the information they provide is the same. Let's see some examples of how to interpret this instrument. In this case, the instrument is indicating a pitch of 0 degrees and a bank angle of 18 degrees to the left. In this other example, the instrument indicates a pitch of 8 degrees nose up and a bank angle of 0 degrees. Here, it now indicates a pitch of 9 degrees nose up and a bank angle of 10 degrees to the right. In this other case, we can see a pitch of 9 degrees nose up and a bank angle of 20 degrees to the right. And in this last one, it indicates a pitch of 2 degrees nose down and a bank angle of 0 degrees. Now, in all of these examples, a conventional bank indicator was used. However, some attitude indicators incorporate a sky pointer as a bank indicator. Basically, a sky pointer is a bank indicator that remains fixed pointing upwards, while the banking scale is the one that moves to indicate the bank angle. As a consequence of this design, when the aircraft starts banking to one side, the sky pointer will move to the opposite side. In this example, as we can see, the aircraft is banking to the right, while the bank indicator is on the left side of the scale. This can be quite confusing for some pilots, especially those who usually fly with conventional bank indicators. Let's see in more detail how a sky pointer works. In this example, we can see the sky pointer indicating a bank angle of 0 degrees. Now, let's suppose the aircraft starts banking to the left. As we can see, the miniature aircraft shows the left bank correctly. However, the bank indicator is on the right side of the scale. The opposite happens if the aircraft banks to the right. In this case, the miniature aircraft shows the right bank correctly, but the bank indicator moves to the left side of the scale. The key to avoid confusion when reading this instrument is to use the bank indicator only to determine the angle and use the miniature aircraft to determine the direction of banking. Now, another feature of some attitude indicators, especially those manufactured in the United States, is an adjustment knob. It allows the pilot to adjust the miniature aircraft with the instrument horizon according to the pilot's point of view and the attitude of the aircraft when flying straight and level. Here we can see an example of how the miniature aircraft moves when the adjustment knob is rotated. However, a problem with this design is that an inadequate adjustment of the miniature aircraft can cause problems in the indication of the actual attitude of the aircraft. Especially when flying in IMC conditions or during the night, since there are no visual references to confirm the attitude of the aircraft. For these reasons, some civil aviation authorities in other countries have decided to prohibit or restrict the use of this adjustment knob. Despite this, there are many aircraft today that incorporate this feature, so as a rule of thumb, the miniature aircraft should only be adjusted on the ground or when flying straight and level in VMC conditions. Another component that can be found on some instruments is a red flag, which is visible when the instrument's gyroscope is not working properly, thus indicating that the instrument should not be used. So far, we have seen the parts of the instrument and how to read it. Let's now see how it works internally. As we already mentioned, the attitude indicator uses the gyroscopic effect of rigidity in space to measure the attitude of the aircraft in relation to the horizon. This instrument incorporates a vertical gyroscope so that the plane of rotation is parallel to the real horizon, as we can see in this image. Apart from this, the gyro has 3 degrees of freedom, which means that it is free to rotate in all 3 axes. This implies that, once aligned with the real horizon, the gyro will remain rigid in space, regardless of aircraft movements. That's why it is an excellent reference for measuring the attitude of the aircraft. Let's now see how the pitch attitude is measured using this gyro. On the right side we have the instrument as the pilot would see it, while on the left side we see the instrument from the side. Inside we have the gyro, whose plane of rotation is parallel to the horizon. In this case, the instrument is indicating a pitch attitude of 0 degrees. Let's suppose now that the aircraft pitches up. In this case, both the aircraft and the instrument will pitch up, while the gyro will remain rigid in space, aligned with the horizon. This way, the instrument can measure and show the current pitch attitude of 15 degrees nose up. The opposite way, if the aircraft pitches down. Both the aircraft and the instrument will pitch down, while the gyro will remain rigid in space, aligned with the horizon, thus measuring and indicating the current pitch attitude of 20 degrees nose down. Let's now see the bank indication. Here, in both cases we see the instrument from the front side. Inside we have the gyro with the plane of rotation aligned with the horizon. In this case, if the aircraft starts banking to the right, both the aircraft and the instrument bank to the right, while the gyro remains rigid in space, allowing to measure and indicate the current bank angle of 30 degrees. An additional fact regarding this example is that the bank indicator is a sky pointer, so although the aircraft banks to the right, the indicator is on the left side of the scale. Now, the opposite happens if the aircraft banks to the left. In this case, both the aircraft and the instrument will bank to the left, while the gyro remains rigid in space, aligned with the horizon, thus allowing to measure and indicate the current bank angle of 30 degrees. Now, although this instrument is very useful for determining pitch and bank attitude quickly and accurately, it has some limitations. And it is that, although theoretically the instrument's gyro has 3 degrees of freedom, in reality it has mechanical stops that prevent the gyro from rotating completely freely. This means that if the aircraft reaches excessive pitch or bank angles, the mechanical stops will prevent the gyro from rotating freely, causing the instrument to topple and become inoperative for a few minutes while it realigns with the horizon. Here is an example of what happens if the pitch or bank limits are exceeded. On older instruments, it is common to find pitch limits of 60 degrees and bank limits of around 100 degrees. While in the more modern ones we can find less restrictive limits of 85 degrees of pitch and no bank limits. Now, another effect that is present in this instrument is the gyroscopic apparent wander. Let's try to explain it simply. When a gyroscope starts spinning, it will tend to remain rigid in space. However, the thing is that the Earth does not remain stationary, it rotates at about 15 degrees per hour. This implies that the plane of rotation of the gyro will progressively drift from the real horizon. In a vertical gyro such as the attitude indicator, This effect is maximum at the equator and minimum at the poles. Let's see a graphical example of why this happens. Let's say we are at the equator, in this yellow point, and we turn on the instrument at 4 p.m. This way, the plane of rotation of the gyro is aligned parallel to the horizon. Now, past 1 hour, at 5 p.m., the Earth will have rotated 15 degrees, while the gyro remains rigid in space in its original position. So if we measure now the angle between the actual horizon and the plane of rotation of the gyro, we will find that it is 15 degrees. Which means, in other words, that the attitude indication of the instrument will be incorrect by 15 degrees. As we can see, this effect worsens with time. So at 6 p.m., the Earth will have rotated another 15 degrees, so now the difference between the horizon and the plane of rotation of the gyro will be 30 degrees, and so on. It is therefore important that the plane of rotation of the gyro realigns itself constantly, so it remains parallel to the horizon. To do so, it incorporates a mechanical control system that uses the Earth's gravity to keep the plane of rotation parallel to the horizon at all times. In air-driven gyros, a pendulous vanes system is used, while in the electrical-driven ones, an electrical torque motor is used. However, we will not go into detail on how these control systems work, as they are not operationally relevant. Now, some electrical-driven attitude indicators incorporate a caging knob that allows decoupling the gyro from the instrument face. This prevents the gyro from toppling during excessive attitudes or maneuvers, as it will act as a free gyro without mechanical stops. This knob is also used to quickly realign the gyro with the horizon in case it is toppled. However, this procedure should only be done in straight and level flight or on the ground to ensure an adequate alignment. We will talk about the attitude and heading reference system, which, like the air data computer, has helped the transition from the conventional analog instruments to the new digital systems. However, before going into detail with this system, we must see how conventional analog instruments work. In the case of gyroscopic instruments, each one has its own gyroscope specifically designed to measure a certain parameter. This means that each instrument has its own gyro, gimbals, gears, and other moving parts. This results in more complex isolated systems, with errors and inaccuracies due to mechanical imperfections, friction, gyroscopic drift, among others. And in addition to this, in the case of the heading indicator, the crew must manually correct the indication using the magnetic compass as a reference. And to do so, the aircraft must be flying in straight flight with a constant speed, as these are the only conditions under which the compass gives a correct heading indication. All this results in higher workloads and lower accuracy. As we have seen, these conventional gyroscopic instruments tend to have low accuracy and several disadvantages. So in order to improve the accuracy and functionalities of the system, the attitude and heading reference system was developed, which is abbreviated as AHRS. This unit has gyroscopes, accelerometers, and magnetometers oriented in the 3 axes. These sensors calculate the aircraft attitude and heading accurately in real time, based on the measurement of the movements of pitch, bank, and yaw. Then the information is sent electronically to the relevant instruments and systems. Now, since the resulting parameters are generated electronically, these are easily integrated with different types of instruments. For example, the electronic data generated by the unit can be used to feed analog instruments that are adapted to receive electronic inputs. Or they can also be sent to electronic flight instrument systems with digital presentations. The instruments normally fed by the AHRS are the attitude indicator, the heading indicator, the turn and slip indicator, and the turn coordinator. And apart from this, the system can also feed instruments that previously used a remote indicating compass, such as the HSI or the RMI. Here we see the instruments in their conventional analog presentation. However, normally this unit is used in conjunction with digital instruments, as we can see here. Here we can see the attitude indicator, the slip and skid indicator, the HSI, and the RMI. And although the main purpose of the AHRS is to feed the flight instruments, the information can also be sent to other systems that require it, such as the autopilot and flight director system, the yaw damper, the weather radar, the monitoring and warning system, the flight management system, the flight data recorder, and the ACARS. Now that we have seen the instruments and systems that use the information generated by the AHARS, let us now look at its sensors. The AHARS has a series of sensors contained within an inertial measurement unit, abbreviated as IMU. This unit is responsible for measuring changes in the aircraft's attitude and heading, and then sending this raw information to a Kalman filter and a processor to integrate and process it. After this, the electronic data is sent to the flight instruments and systems. Now, this was a basic overview of how the IMU works. Let us now take a closer look at how the IMU detects changes in attitude and heading. Normally, this unit has 3 accelerometers, 3 gyroscopes, and 3 magnetometers oriented on the 3 axes. These axes are known as X, Y, and Z respectively for the movements of roll, pitch, and yaw. This means that there is one accelerometer for each axis, which allows to calculate the accelerometer's derived attitude. The same happens with the gyroscopes, there is one for each axis, which allows to calculate the gyro-derived attitude. And finally, there is also one magnetometer for each axis, which allows to calculate the magnetometer's derived heading. With this in mind, and taking into account the capabilities of each type of sensor, we would obtain the following data. The accelerometers are capable of measuring the attitude of the aircraft in terms of pitch and bank. The gyros are capable of measuring the pitch, bank, and heading. And the magnetometers are capable of measuring only the magnetic heading. All this information derived from the sensors is sent to a Kalman filter, which integrates and complements this information in order to obtain a sensor fusion. This sensor fusion improves the integrity and accuracy of information to then calculate the estimated pitch, bank, and heading values. Now, it is important to mention that each IMU is different since each unit is designed depending on needs, applications, and budget. Therefore, there are different technologies used in inertial sensors. For example, laser and fiber optic sensors are normally used in advanced inertial reference systems. While on the other hand, microelectromechanics sensors are widely used in attitude and heading reference systems, and therefore in this video we will focus on this type of sensors. A microelectromechanics system, abbreviated as MEMS, is a compact, relatively simple, inexpensive, and accurate system used to measure the attitude and heading. That is why they are easily incorporated into wireless and mobile devices, for example to provide the compass or inclinometer functions of some smartphones. With this in mind, let's now see how each of the sensors of a MEMS system works. Starting with the accelerometers. A MEMS accelerometer consists of a mass attached to calibrated springs that moves back and forth depending on the acceleration it experiences. This way, the displacement of the mass can be measured and interpreted as a measure of acceleration. The information from the accelerometers is vital, for example, for the initial alignment of the system, since they can detect the direction of gravity and use it as a reference to establish the position of the horizon. Apart from this, accelerometers are also useful for measuring changes in the attitude of the aircraft in terms of pitch and bank. Now, a MEMS gyroscope consists of a mass attached to calibrated springs that constantly moves back and forth. This way, when a rotation around the measured axis occurs, the mass is displaced to a side due to the Coriolis force. This displacement of the mass can be measured and the angular rate can be determined, just like when the precession is measured in a conventional gyroscope. In essence then, a MEMS gyro is not actually a real gyro. Since instead of measuring rotation on an axis using the gyroscopic principles, the MEMS system calculates it based on the resultant forces when a rotation occurs. However, it is called a gyro because the information it provides is basically the same. Finally, a MEMS magnetometer consists of a plate with high electrical conductivity attached to a direct current circuit. In this case, the Earth's magnetic field will influence the behavior of the electrons as they flow through the plate. This way, If the voltage between 2 points in the plate is measured, the resulting value will depend on the strength and direction of the magnetic field, thus allowing to measure it in the 3 axes. However, in aviation we have a big problem with this type of magnetometers since they are affected by electromagnetic interferences from the avionics or the engines. So, to solve this, instead of using the magnetometers of the IMU, the AHRS can receive information from a remote flux valve, which we have already discussed in detail in the video about the remote indicating compass. And just like in a remote indicating compass, some AHRS incorporate a free mode that allows the magnetometers to be disconnected from the system in areas where magnetic heading information is unreliable, as for example near the magnetic poles. In this case then, the heading information will only be provided by the MEMS gyros, not the magnetometers. Now, since we have seen how the sensors of a MEMS system work, we must say that the Kalman filter allows for error compensation, since by using the joint data derived from the accelerometers, gyroscopes, and magnetometers in all 3 axes, errors due to gyroscopic drift and other imperfections can be almost completely eliminated. This substantially increases the accuracy of information and reduces crew workloads, since it is not necessary to perform manual corrections. Now, in order for the AHRS sensors to function properly, an initial alignment is required. The purpose of this initial alignment is to determine the attitude of the aircraft when it is on the ground, since changes in attitude will be measured in relation to the attitude detected during this initial alignment. This process normally takes a few seconds. However, it can take up to a couple of minutes depending on the manufacturer of the AHRS system. An important consideration during this initial alignment is that the aircraft must remain stationary on a level surface so that the initial reference attitude is as accurate as possible. Now, this alignment is required only upon power-up. However, if there is a problem with the unit during flight, a realignment may be required. In this case, the aircraft must remain in straight and level flight at constant speed and follow the instructions of the manufacturer for the realignment. Now, in the event of a total failure of the AHRS, an alert will be displayed on the affected instruments as we can see here. In this situation, in aircraft equipped with a single AHRS computer, the crew must use the standby analog instruments. These standby instruments use conventional mechanical gyroscopes independent of the AHRS sensors, so they are not affected by the failure of the unit. Now, talking about the system layout, smaller aircraft with simple systems usually have only one AHRS computer. In this case, the IMU sensors send the raw data to the Kalman filter and processor of the AHRS, and then the unit sends the processed electronic data to the relevant instruments. And separately the standby instruments are driven by mechanical gyroscopes. Now, in aircraft with 2 sets of instruments, 2 AHRS are normally installed, each fed by its own IMU with dedicated sensors. This means that there are 2 AHRS, one for the captain's instruments and another for the first officer's instruments. And apart from this, there are also the standby instruments driven by mechanical gyros. And as with the air data computers, when there is more than one AHRS unit installed, although each one is independent, they are interconnected so that the information calculated by each unit can be compared to detect failures or inaccuracies of the sensors. And in addition to this, there is also the possibility to select the AHRS that feed a certain group of instruments. For example, if here we have this configuration and the AHRS number 2 fails, then the crew can select the AHRS number 1 to also feed the first officer's instruments so they can work properly. Now, as with the air data computer, in more complex and modern aircraft, the AHRS is integrated with other computers and units to complement the information and calculate other useful parameters. For example, it can be integrated with an air data computer, obtaining the air data, attitude and heading reference system. This new unit allows increasing the accuracy of attitude information, gives a more stable vertical speed indication, and compacts 2 units into one. It is also common to find this unit integrated with a global navigation satellite system, which allows to calculate other parameters such as wind direction and speed, the ground speed, the wind correction angle, and the magnetic track. An example of the use of this type of unit is the Garmin G1000, which, although it does not use the units combined, it does use the information derived from each one to calculate all the parameters. Finally, with the advent of smaller and cheaper MEMS sensors, portable AHRS units that transmit information wirelessly through Wi-Fi or Bluetooth became available in the market. These can be used to provide accurate data to mobile navigation applications, such as ForeFlight or Air Navigation Pro. And although smartphones and tablets already incorporate MEMS sensors, their accuracy and reliability is much lower compared to the portable AHRS units. We will talk about the turn coordinator. This is one of the basic flight instruments that we will find in any aircraft, and its operation is based on the gyroscopic principles. As mentioned in the video about the gyroscopic system, most of the light aircraft have the following configuration. The vacuum pump provides suction to drive the gyros of the attitude indicator and the heading indicator, while the gyro of the turn coordinator is driven by direct current from the aircraft electrical system. With this in mind, it is important to mention that this instrument comes in two main variants: the turn coordinator and the turn and slip indicator. Although both have the same principle of operation, the information they provide and the way it is presented are slightly different. Let's first look at the turn and slip indicator. This instrument indicates whether the aircraft is making a turn and how fast the heading change is occurring, which is the rate of turn. Something important to note is that this instrument does not indicate the bank angle of the aircraft, it only shows the direction of the turn and the rate of turn. Now, this instrument has another function since it incorporates an inclinometer at the bottom, which allows to measure the quality of the turn. In other words, it allows the pilot to know if the aircraft is flying coordinated, skidding, or slipping. But before we see how it works, let's look at the parts of the turn and slip indicator. In the upper part we have the rate of turn scale with its corresponding needle. And in the lower part we have the liquid-filled capsule of the inclinometer and a solid ball which is free to move within the capsule. Let's take a closer look at the rate of turn scale and how to interpret it. Here, the center mark represents straight flight, or in other words, a rate of turn of 0 degrees per second. On the other hand, the side markings represent a rate of turn of 3 degrees per second, which in aviation corresponds to the standard rate of turn. It is mainly used in instrument flight procedures, as well as in many maneuvers. This standard rate of turn allows the aircraft to make a 360-degree turn in 2 minutes, which is specified on the instrument as we can see. Let's now see how to read this instrument by means of an example. Here, the needle is pointing the center mark, which means that the aircraft is flying straight, with a constant heading. In other words, the rate of turn is 0 degrees per second. Now, if the needle moves this way, we can see that the aircraft is turning to the right. And since the needle is pointing exactly the side mark, this means that the rate of turn is 3 degrees per second. In the same way, if the needle points the left mark, it will represent a turn to the left at 3 degrees per second. Now, if for example the needle moves to this other position, we can see that the aircraft is still turning to the left, but with a slower rate of turn, in this case, less than 3 degrees per second. And on the other hand, if the needle moves to this other position, beyond the mark, it will indicate a turn to the left with a rate of turn of more than 3 degrees per second. We have already seen how to interpret the turn indicator, now let's see how to read the inclinometer. In general terms, we can say that it allows to measure the quality of the turn. The inclinometer is the simplest instrument that we will find in an aircraft since it consists of a capsule filled with liquid and a ball that is free to move inside. In this case, if the ball remains centered in the capsule, it will indicate a coordinated flight. If the ball moves to the side of the turn, it will indicate a slipping turn. And if the ball moves to the opposite side of the turn, it will indicate a skidding turn. For example, here we can see that the instrument indicates a turn to the right, and since the ball remains in the center, we say that the aircraft is making a coordinated turn to the right. If in this situation the ball moves to the right, which is to the side of the turn, it will be indicating a slipping turn to the right. And if the ball moves to the left, which is the opposite side of the turn, it will indicate a skidding turn to the right. Usually, in most procedures and maneuvers, the objective is to maintain a coordinated flight, so the pilot must keep the ball centered. To do so, a rule of thumb is to step on the ball, which means that in order to correct a skidding or slipping turn, the pilot must press the pedal on the side of the ball to center it. However, we will not talk about this flight technique in detail in this video. Let's see now how does this instrument work internally. The turn and slip indicator uses the principle of gyroscopic precession to measure the rate of turn. To do so, it incorporates a horizontal rate gyro, which is restricted in one of its axes. As we can see, the plane of rotation of the gyro is perpendicular to the horizon, as was the case with other instruments, such as the heading indicator. However, the difference is that this is not a free gyro. Since it has only 2 degrees of freedom, which means that it is not free to rotate on one of its axes. And if the gyro attempts to rotate in the axis that is restricted, it will precess. And measuring that precession is an excellent way to determine how fast the aircraft is changing its heading. And that is exactly what the instrument does. But let's see how it does it. Here, in the image on the left we can see the gyro from above, while on the right side we have a side view. If in this case the aircraft starts turning to the left, it would be as if we were applying a force to the gyro at this point. However, due to the precession effect, that force will be exerted at 90 degrees in the direction of rotation of the gyro, which means that it will actually be applied at this point. The result will then be that the gyro will be tilted in this way. Obviously, the faster the heading change, the greater the precession and the tilting of the gyro. And then the movement of the gyro is directly transmitted to the needle on the instrument, indicating this way the direction and the rate of turn. Clearly, the gyro will not be able to tilt beyond a certain limit, since a system of calibrated springs will limit the gyro movement and return it to its neutral position when the aircraft stops turning. This system allows to accurately measure the rate of turn and return the needle to the straight flight indication when the turn finishes. Let's see some examples of this. Here the aircraft is flying straight, so the gyro remains in the neutral position, making the needle to point the center mark. Now, if the aircraft starts turning to the right, the gyro will tilt due to precession, moving the needle of the instrument to indicate a turn to the right. This will happen as long as the aircraft continues to turn, because when the aircraft stops turning, the precession will stop and the springs will return the gyro to the neutral position, making the needle to point the center mark again, indicating a straight flight. In the same way, if the aircraft starts turning to the left, the gyro will tilt due to precession, making the needle to indicate a turn to the left with the corresponding rate of turn. This will happen until the aircraft stops turning. Then the precession will stop, and the springs will return the gyro to the neutral position. We have already seen how the turn indicator works. Let's now see the principle of operation of the inclinometer. Basically, the inclinometer consists of a ball that is free to move inside a slightly curved capsule filled with liquid. With this design, the ball will move depending on the balance between centripetal and centrifugal force during a turn. For example, if the aircraft starts turning to the right, the ball will be subjected to the centripetal and centrifugal forces generated during the turn. If these forces are equal, the ball will remain in the center of the capsule. But if there is an imbalance between these forces, the ball will move to one side or the other. This results in 3 possible situations. The first one is the coordinated turn. We say that a turn is coordinated when the centrifugal and centripetal forces are equal. Here we can see the forces acting on an aircraft during a coordinated turn. And since the centrifugal and centripetal forces are balanced, the ball of the inclinometer will remain centered. The other possible situation is the skidding turn. A skidding turn is produced when the centrifugal force is greater than the centripetal force, as we can see in this image. What will happen in this case is that the ball will move to the opposite side of the turn. For example, this aircraft is turning to the left and the ball moves to the right. Again, this happens due to the imbalance between centrifugal and centripetal forces. The last possible situation is a slipping turn. A slipping turn is the opposite to a skidding turn. It occurs when the centrifugal force is less than the centripetal force, as we can see in this image. In this case, the ball will move to the side of the turn due to the imbalance of forces. So in this example, the aircraft is turning to the left and the ball moves to the left. As we could see, the inclinometer is a pretty simple instrument since it consists only in a ball that is free to move inside a capsule, and therefore it does not rely on other systems to function. Let's now move on to the other variant of this instrument. The turn coordinator. The principle of operation of this instrument is almost identical to the turn and slip indicator that we have just seen. However, it has a slight difference, and it is that, when starting or finishing a turn, it also indicates how fast is the aircraft banking, not only the rate of turn. However, despite having this additional functionality, we must emphasize that this instrument does not indicate the bank angle. For that, we will have to use the attitude indicator. With this being said, let's see the parts of the turn coordinator. Here, the main difference in relation to the turn and slip indicator is that instead of having a needle, we have a miniature aircraft. And therefore, the rate of turn markings are located at the sides. And as in the turn and slip indicator, at the bottom we have the inclinometer. Let's take a closer look at the rate of turn scale of this instrument. Here, the upper marks represent a rate of turn of 0 degrees per second, or in other words, straight flight. While the lower marks represent a rate of turn of 3 degrees per second, which, as with the turn and slip indicator, will allow the aircraft to make a 360-degree turn in 2 minutes. Now, an important thing to keep in mind with this instrument is that although it has a miniature aircraft, it does not provide pitch information, as stated on the instrument dial. Let's now see some examples of the operation of the turn coordinator. Here we can see that the wings of the miniature aircraft are leveled, pointing the upper marks, therefore indicating a straight flight. If the miniature aircraft now moves this way, we can see that it is inclined to the right in such a way that the wing points to the lower mark. This indicates that the aircraft is turning to the right at a rate of 3 degrees per second. The same happens if the aircraft turns to the left. In this case, the instrument is indicating a turn to the left at a rate of 3 degrees per second. Now, if for example the miniature aircraft moves to this new position, since the wing is beyond the mark, it will indicate a turn to the left at a rate of more than 3 degrees per second. And if for example it moves to this other position, it will indicate a turn to the left at a rate of less than 3 degrees per second. Having seen how to read this instrument, let's take a look at how it works internally. As with the turn and slip indicator, the turn coordinator uses the principle of gyroscopic precession to measure the rate of turn. And although it also incorporates a horizontal rate gyro, the difference is that it is tilted 30 degrees. This means that if we compare the internal mechanism of a turn and slip indicator and a turn coordinator, we will see that the gimbal of the turn coordinator is tilted 30 degrees. This inclination of the gimbal allows the gyro to also be sensitive to the banking motion, not only to the heading changes. Apart from this, both instruments are practically identical. Let's see some examples. Here the aircraft is flying straight, so the gyro remains in the neutral position, and the wings of the miniature aircraft are leveled pointing the upper marks. If the aircraft starts turning to the left, the precession caused by the heading change and the banking motion will cause the gyro to tilt this way, moving the miniature aircraft to indicate a turn to the left. This will happen as long as the aircraft continues to turn, because when the aircraft stops turning, the precession will stop and the springs will return the gyro to the neutral position, leveling the wings of the miniature aircraft. If now the aircraft starts turning to the right, the gyro will tilt to the opposite side due to precession, causing the miniature aircraft to indicate a turn to the right. And when the turn finishes, then the precession will stop and the springs will return the gyro to the neutral position. Finally, we have to mention that in the case of instruments driven by direct current, they incorporate a red flag which is visible when no power is being received, and therefore the instrument should not be used. I hope the information presented in this video was useful. If so, don't forget to share, like, subscribe, and leave a comment down below. Thanks for watching.